Now let's look at what happens when we apply the absolute value operation to a function. Now, the absolute value operation is an interesting one because it's actually two functions in one. If x is positive, or the value inside the absolute value bars is positive, then we treat the information differently than if the value inside the absolute value bars is negative. So when we have different rules for different situations for a function, we call that a piecewise function. And here's how we would express a piecewise function using function notation. We break each function into a series of instructions, and then we follow those instructions with the domain where we are allowed to apply those instructions. So in the case of the absolute value, if we're given a function f of the absolute value of x, we would use x in the function if x is positive or greater than or equal to 0. However, if x is a negative value, then for the equation, we would replace every x with the negative of x. So if x were negative 3, we would replace it with the negative of negative 3, or positive 3. And that would be true for all values of x less than 0. So we start by expressing the rule, and we follow that with the domain where that rule would apply. So let's see how this absolute value with differing rules would affect the graph of a function. Let's start with a simple parabola, f of x equals x squared minus 4x plus 3. Now, if we put that into our calculator, why don't we all do that? We should get a graph that looks like this, with a y-intercept of 3 and x-intercepts at 1 and 3. So the first thing I'm going to do is apply the absolute value operation to the whole function. So g of x equals the absolute value of f of x. In explicit terms, this is what it would look like. Now, how would that affect my graph, you ask? Well, let's find out. First of all, since we would look at the y values that are produced by the expression x squared minus 4x plus 3. If I end up, after plugging in an x value, with a positive y value, there's no reason to change it. And here are the values on the graph where y is already positive. However, if I end up with a negative y value after plugging in x, I have to take the absolute value of that negative number, and so that negative number now becomes positive. I'm multiplying my original value by negative 1. And we just learned what happens when we multiply our function by negative 1. We end up with a reflection across the x-axis. So this whole area down here where x is negative, or where y is negative, now creates a graph where y is positive. This is a much prettier picture than what I drew. But you can see the original function in red. All the positive red values stayed the same, but the negative red values were reflected to those new blue values. So the other way we could apply the absolute value operation in my function is to take the absolute value of every x in the equation before determining our y value. All right, well, let's start with our original graph and think about how that operation would affect the graph. So, if x were already positive in my equation, and I plugged it into this expression for h of x, for instance, 3, it wouldn't change what happened if I didn't have the absolute value bars. So everywhere that x is positive, I should continue to have the same graph. No change. Now when x is negative, I won't get the same y value because I'm changing x to its positive partner. So if x started out as -3, the first thing I would do is change it to +3. And I would get the y value for +3 when I plug in -3. So for every negative value, I should get the same value I got from the positive value. A mirror reflection of that positive image that I've traced here in black. So I should get something like that. Now these original values for y when x was negative no longer exist in my new graph because I can never actually use a negative number in my expression. So in a much more aesthetically pleasing graph, we can see that for the original red graph, the portion to the right of the y-axis is still there. The portion to the left of the y-axis has been eliminated in my new absolute value transformation. And what's been added to the graph is a reflection of the positive side into the negative half of my graph. So if we wanted to talk about this effect, we could say that if g of x is equal to the absolute value of the entire function f of x, what's going to happen is that my original function is unchanged if my original function is non-negative. So for all positive y values of x, no change. However, we get a reflection across the x-axis of my original function if my original function is negative. If I take the transformation f of the absolute value of x, then what remains unchanged are the non-negative values of x. So not the non-negative values of y, but the non-negative values of x. Everything to the right of the y-axis remains unchanged. To the left of the y-axis, negative values of x, we reflect the part of the graph for positive values of x. So we take a mirror image or reflection across the y-axis of everything that was on the positive side originally. The part that was on the negative side originally is simply eliminated.